This class we're going to talk about plane strain. We already talked about plane stress, and we know that plane stress is we talk something's very very thin, and plane strain is something very very thick. So let's fix some thoughts here. As we previously spoke, if I have something very 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 thin and I have something very 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 thick, typically what happens is when I apply a load in this direction, let's suppose this is simply supported for the sake of an argument for this particular example, and I'm applying a load here. This does not have enough strength, enough energy to oppose that load, so therefore this is going to deform, and this means this is a case of plane strain, plane stress. Now here in this in the other case, I have a load applied, and you can see that my stresses, they're going to be stresses are going to form, and it's going to absorb that energy, and the deflection is going to be very very small. So therefore, this is called a case of plane strain. Sorry. So in this case, sigma zz is not equal to 0, but ezz is equal to 0. If I said this is the z direction, we said this is the z direction. The same here, sigma zz is 0 and ezz is not equal to 0. So what do the equations look like? So first of all, let's start with the general case. You may want to pause this video if you want to, and you can take a notes of this. This is a very nice, convenient form of writing this in a matrix form, and it comes nothing else from the equation 3.19 of your textbook. Just writing in a matrix form, you can get it like, you can write it in the following form. So what he's basically saying is, if I know my stresses, I can find my strains. And this is the Poisson's ratio, the Young's modulus, and you can see this is actually equal to this. It's identically the same. And this is just more general, but it includes all these stresses. Now, the second case is what happens when I have the inverse of the Hooke's law. When we are working with the case of the inverse of the Hooke's law, then this is what your general equation looks like. This is xz, and this will be yz. This is xz. XX, YY, ZZ, XY, XZ, and YZ. And this is the inverse. So what you're saying here is, if I know my strains, I can find my stresses. Now, there are a couple of variations of this that we need to take into account, because if it's a case of plane stress, you have to make small, it's not that simple, because you will have to set this equal to 0, eliminate that row, and replace it in the first two equations. By doing that, what you can show is, if we are working for the case of plane stress, as for an example, just for this sake of this argument, let's suppose I'm confined to the XY plane. Okay. Remember, I could be confined to any other plane, but we are just saying it's confined to the XY plane for this argument's sake. So I already told you here, sigma zz is 0, but I told you that ezz cannot be 0. So let's show that. In order to do that, what we're going to do is we're going to use the following equation. Okay. Sigma xx, sigma yy, tau xy. So this is given, and I want to find exx, eyy, ezz, and gamma xy. So I need to find this. Okay, this is the goal if it's a plane stress. So let's just work with the normal stresses for a moment. The shear is easy as before. So the Hooke's law, the inverse form of the Hooke's law still applies. And this is the minus Poisson's ratio, minus Poisson's ratio, minus Poisson's ratio. And this is sigma xx, sigma yy, and for plane stress, because confined to the xy plane, this is equal to 0. So if I multiply this, you can show that this is actually equal to sigma xx minus nu times sigma yy, sigma yy minus nu sigma xx. This is equal to minus nu sigma xx plus sigma yy. And you can immediately see what's really going on here, that your last term, you can see that it's not equal to 0, and this is what corresponds to EZZ. And the guy that's guilty of making sure that this is not 0 is the Poisson's effect. Remember what the Poisson's effect says, that if I can have a bar, just for an example, and I apply stress, I pull it from both sides, then this is going to stretch, but at the same time this is going to contract, and the effect of this is because of the Poisson's ratio. Okay, so with that said, this is quite straightforward. And yes, and don't forget your gamma xy is nothing else than tau xy divided by g. That doesn't change. Just wanted to show you that this will not be 0. Now, the other equation that we have is a little bit different. Is for the case of plane strain. Now, plane strain, we can derive the equations, and I'm going to save the derivation, keep the derivation out of this. But for the sake of this conversation, let's suppose your plane strain is confined to the xy plane. Remember, this is gamma xy divided by 2, eyy, 0, 0, 0, 0, 0. Okay? So we see that EZZ is equal to 0, and sigma ZZ, I told you, cannot be 0. So let's just show you that. So in such a case, if I want to find my sigma, so the problem basically is saying, I know this, I know the strains. Remember, this is 2 times EXY. I know this, and I am interested in finding, from knowing this, I want to find what sigma XX, sigma YY, sigma ZZ, and tau XY is. Okay, so the equation is a bit different. So let me just show you what the equation looks like. Sigma XX, sigma YY, sigma ZZ on this side. And that's going to equal to E. This is only for plane strain. Okay. 1 minus nu, 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 1 minus no, 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 1 minus no. And then this is going to equal to exx, eyy, ezz, which we know that's equal to 0. Okay, so this guy is 0. If I multiply the whole thing, what you can show is that you get the following expression. And so multiplying the first term, 1 minus nu times exx plus nu times ezz, eyy, sorry. This gives you nu times eyy plus 1 minus nu exx. The last term is nu times exx plus eyy. And once again, what you can see is the value that I'm looking for is right here, and it is because it's a PlaneStrain problem. So the problems in which you can identify that we are confined to a plane, we want to use this type of equation, this version of the equation. When we know the problem is plane stress, then we need to use this form of the equation because this is what we're interested. If you realize this is nothing else than your standard form, and for the plane strain problem, when it's a plane strain, that this is the type of equation that I'm actually using to solve for this. So this concludes our discussion on PlaneStrains.